morning. My name is Adithya Rao, and I'm here to talk about our work here, actionable and political text classification with word embeddings and LSTM. This work was done at Lithium Technologies with my colleague Nemanja Spasovic, who's sitting there. So basically, we heard Professor Tang talk about sentiment analysis and opinion mining. Here, in this work, what we are trying to show is that basically there are a lot of problems that go beyond just sentiment recognition. So in particular, we try to look at applications where just knowing the sentiment is not sufficient to get useful insights. In particular, we look at two problems, which is actionability for customer service and political leaning on social media. I'm sorry, are the slides too small? Maybe I can just... We look at these particular problems, actionability on social media and political leaning. The way we solve this problem is using deep learning methods, where we use word embeddings and LSTM techniques to infer these higher level concepts. We show that with these kinds of methods, we get around 85 to 91% accuracy on various different languages when we apply it to actionability as well as political leaning. The advantage of using deep learning here is that it, first of all, performs a lot better than traditional models where when we say traditional, we mean supervised learning techniques where you have to have like manual features that you generate. So we show that these models are actually perform much better than that. Another interesting thing is that this also allows portability of models where the same technique can be applied to different kinds of problems with similar results. So this is pretty useful when you are trying to build like a particular model that applies across different kinds of problems. And finally, we also show that basically the models that we built here for actionability are actually used in production at Lithium Technologies. And the political leaning model that we've built is actually open for download in case you're interested. So why solve these problems, first of all? So these problems come from, let's say, you are a customer service provider. You have some very real problems to solve, such as customers are complaining and you need to solve their complaints. So how do you go about doing it? Traditionally, what people did was that you had these call centers where people used to call in saying that, hey, Comcast, my internet is not working, please fix it. But this has like a very real cost because you need to hire a person to sit behind the call and take these calls and pay them salary and so on. So with social media, this became a lot easier over the last few years. It's easier for a customer to go and say that I have a certain complaint, and it's easier for the service provider to even immediately respond to that user by just having like a person type in like a good response. So online customer support has become a pretty big deal for a lot of big corporations in the last few years. Now, let's say you're Comcast and decide, hey, okay, I want to use Twitter to solve my customer complaints. So how do I go about doing that? So maybe the first thing that you would do is say that, okay, go through all of the Twitter data and in Twitter social media tweets as they're coming in and filter out maybe only the tweets which mention Comcast in them. So you could have like a bunch of tweets where Comcast is being mentioned, but then you realize that there are millions and millions of such tweets because people are talking about Comcast all over the place. Now, among these, then again, you need to filter out the ones where people are actually complaining about something so that you can respond to them in a meaningful way. Now, when you talk about user complaints like this, first of all, identifying which are these messages that have complaints in them is itself no easy task. But let's say you were somehow able to do that. Then in that case, would you run something like sentiment analysis on top of that? The problem is like when you're talking about complaints, in general, all of these complaints have a negative sentiment. And that is why they are called complaints. Otherwise, they wouldn't be complaints at all. So because they already have negative sentiment, it's not just useful to know what the sentiment is in this case. So this is a scenario where what you want to actually know is what is some message that is actionable that the user can be responded to versus something that is not actionable and can just be ignored. So this is the kind of problem that we are trying to solve here. And just to make that a little more concrete, so here are some real examples from Twitter that are come up, right? So the first tweet says that Yahoo Care emails that I'm sending out replying to aren't being received. Help. So this is a very clear call to action. It says that I have a certain problem and please help me solve it. So immediately the Yahoo customer care can say, hey, hi Cameron, I'm really sorry for you're having this issue. Are you receiving delivery error messages? Please do something, and so on. So because there was a very clear call to action, the person who's responding to it is able to kind of respond in a very meaningful way. Whereas if you look at some other kind of tweets here that mention Comcast, one of them says Comcast is facing a 100 million lawsuit over its service plan. This is an article from Wired or whatever. But this is not really actionable for somebody who's in customer care because he doesn't care because this is just some news article mentioning Comcast. So in this case, this is a very non-actionable message. Another kind of non-actionable message, even in terms of user complaints, is the second example. Here, the user is complaining about, I don't want to pay for your service when we aren't even getting our money's worth. Now, this is a complaint which is very broad and very general. So a person who's sitting in customer care cannot respond to it in a meaningful way because at most you can say, hey, sorry for it, but you can't really provide a solution to it. So in this case, both the tweets below are considered non-actionable, whereas the tweet in the first case is considered actionable. And notice that the sentiment here may vary across different things. So in the first case, even though it is an actionable message, it doesn't have any sentiment kind of associated. It's more or less neutral sentiment. It's not really saying that Yahoo, you're really bad. It's just saying that I'm not able to get my email to work, so please help. So this is not really a positive or negative sentiment, whereas in the second case, even if you have a negative sentiment, you can't really respond to that complaint. So in this case, we see how in a practical setting, identifying these messages as actionable versus non-actionable is more meaningful than classifying them as negative or positive sentiment. So this is one example of a practical application where such a contextual classification is important. Another one is political leaning. This doesn't really need a lot of introduction. I think everybody who's familiar with US elections must know that there's a Republican candidate and a Democratic candidate, and people fall in either camp based on their political leaning. So in this case, what you want to have is you could have several issues when you talk about politics. And on each of these issues, people could have a varying degree of sentiments. So if you had to really ask a political candidate what he would like on social media, he would say that I would want to identify who are my voters, who are the people who are going to vote Republican or Democrat, and how can I maybe convert certain Democratic voters to Republican voters or vice versa. So in this case, what you want to actually find is not the sentiment of individual text messages, or even the sentiment of a user maybe, but what you want to find is his political leaning. So because there is a lot of mixed sentiments on a lot of various issues, the question is, can we learn a higher level concept of Democratic versus Republican versus just learning whether it's positive or negative sentiment? Again, there are a lot of subtleties involved here as well, because depending on the time of when the study is done, for example, you might have different kinds of sentiment associated with it. For example, in the primaries, when you have candidates within the same party kind of battling each other, they're knowing people, even if you are a Republican, you may attack other Republican candidates. So just having the sentiment there is not very informative. So there are a lot of subtleties involved here, but the question is, can we still do some kind of a good job in trying to understand political leaning? And here is again another example of how we could classify as Republican and Democrat. In the first case, the user is saying that Trump and Pence together are going to have jobs, the great trade deals, real immigration enforcement, zero tolerance for terrorists. And so that's a very Republican kind of an opinion because it mentions a lot of different issues, and it clearly states that Trump and Pence is what this person is going to be voting for. Whereas in the second case, it does not actually mention any candidate, but you still talk about different issues like LGBT, gun violence, disarm hate, and all of these different hashtags and different kinds of policies that are mentioned over here as well. So as a human, you could easily tell that one is Republican and the other is Democrat. The question is, could a model do the same? So the next thing is that, okay, now that we've kind of defined our problems, how do we actually go about solving it? Well, first of all, like everybody mentioned, we need to have labeled data in order to do this. So the answer is, how do we get this labeled data is basically for the case of actionability, at Lithium Technologies, there is a product called Lithium Response, which is a platform for customer service. This is being used by a lot of customers, a lot of big corporations, and so on, where what is done is basically as messages coming from social media, from Twitter, from Facebook, from Google Plus, they go into this platform and they are routed to a company agent who is going to respond to the message. So what we did is over a period of 6 months from November 2014 to May 2015, we looked at all the data that is coming in from this platform. And in this case, this was all before we applied any model to it. So it was essentially unfiltered data that was just based on keyword matching for those particular companies. So in this case, if an agent provided a response, then we label that particular message as actionable. And if the agent was not able to provide a response or just ignored the message, it was marked as non-actionable. So this labeled data allowed us to create around 12 million data points for training and around 3 million test samples. So across several different languages, across almost 30 different languages. So this is the kind of label data that we generated from this tool over 6 months. Similarly, for political leaning, what we did was we leveraged Twitter lists, which are basically crowdsourced lists that tell that certain people belong to certain topical lists. So in this case, any user who appeared in lists like, let's say, the Democrats, was kind of marked as a person with a Democratic leaning, or somebody who came in a list marked Republican was marked as a person with a Republican leaning. So this led us to create a list of around 27,000 users with around an equal distribution between Democrats and Republicans. And this data is also available at the link provided below in case you're interested. And with this list of users, what we can then do is basically sample their messages posted over a period of a few months. So we took 3 months between October and January, and this gave us around 330K training data samples and around 85K test samples. So now that we have kind of our label data for both these problems, we can go about trying to solve it. So the way we solve it is we use deep learning kind of techniques over here. So the question is, why do we use deep learning? Well, in traditional methods, what you would probably do is try to find out certain attributes of the text message, maybe find out like part of speech tagging, maybe do some lexicon approaches, maybe have some rule-based approaches, and so on. But a lot of this requires manual intervention in trying to make the model learn certain things. So it takes a lot of, and even if you did create some of these manual features, it is not guaranteed that it covers a lot of these different aspects. So what we do is we instead use deep learning. Now, deep learning has had a lot of success in a lot of different problems over the past few years. One of the main reasons is that it can learn higher level concepts through non-linearities inbuilt into the network structure. Now, in this case, what we are trying to do is to learn a higher level concept, which is why deep learning is a well-suited a technique for this. Another also interesting thing in the deep learning space is that you do not need to manually create features. As the network is learning, it kind of generates features at each layer, which get combined into higher level features. So this reduces any manual intervention that is needed, plus allows you to learn higher level concepts. So this is why we choose to have kind of a deep learning scenario in this case. Now, the network that we use here is described quite simply. So here we have the input, which is pre-processed. What we do is we take every message from social media and we say that we tokenize it first, and then we maybe generate some statistics like TF-IDF or just the word frequency, and replace the tokens by the index of where it stands in that in a sorted list of TF-IDF or frequency. Now, once we have this kind of a representation, we then transform each message into this indices, into this vector of indices, and then we feed it to an embedding layer. Now, an embedding layer, what it does is it takes like, let's say you had a vocabulary of 20,000 words or 100,000 words. That's a lot of big dimensionality in the space. So what an embedding layer does is that it maps this high dimensionality vector into something that is much smaller and manageable. So you could take it and map it to, let's say, a 128 dimensional vector space, where your indices are now replaced by a 128 dimensional vector that represents with different real valued numbers in the vector. So what this allows you to do is then you can feed this feature vector to your to the rest of the network. So the meat of this network is at the LSTM layer. So the LSTM layer stands for the long short-term memory. Now, deep learning comes in many flavors. So when you have, let's say, a lot of spatial data to consider, you would probably use something like convolutional neural networks because they learn spatial dependencies very well. When you want to have text-based kind of learning, text-based are inherently a sequential kind of data. So, which means that what you need to do is you want to learn temporal relationships, and for this case, recurrent neural networks have shown a lot of promise in kind of understanding these temporal relationships. Now, recurrent neural networks in their original form suffer from the problem of vanishing and exploding gradients as you backpropagate these errors. So instead, what a variation that was introduced a few years ago was this thing called long short-term memory. Now, what that does is basically it persists information in a cell state, and the inputs and outputs are modulated by an input gate to the cell state, an output gate, and a forget gate. So by modulating these gates, you're able to tell the network to either remember something, keep something in the cell state for a certain period of time, or you forget it and pass it on to the next unit, and so on. So the LSTM layer here has a bunch of LSTM memory units that kind of persist information and learn these different features. So the reason this is a deep network is because you can think of different time steps as each layer in a network. So if let's say you were looking at a vector that is 50 units long, then you could say that, okay, at each time step, I'm going to feed one token, which means that over 50 time steps, you actually have 50 layers of inputs that you've fed to the network. So that is what makes this a deep network based on the kind of number of LSTM units that you have. Now, once you have this, you also want to have some layers to prevent overfitting, which is the dropout layer. The dropout layer randomly drops a certain fraction of the connections, which allows the network to become more robust and to kind of minimize overfitting in this case. And finally, the fully connected layer is the layer that learns the nonlinearities based on the features that were generated by the LSTM and dropout layers. The loss that we use here is basically a binary cross entropy loss, because the problem that we are considering is a binary classification problem for the most part. And the learning is performed by backpropagating the gradients to train and learn these different weights. So how does this actually perform? So once we have all this model set up, we train these models, and what we did was we trained these models on 30 different languages for the case of actionability. So this table shows some results in terms of actionability as how well it performs. So we see that when for some of these languages which have more data, for example, English, Spanish, and German, we see a kind of a decent performance with around 84-85% accuracy. In some cases, when for languages such as Swedish, we are actually getting close to more than 90% accuracy in this case. In some cases, like Arabic, we are not able to perform that well, and we get around 79%, 80% accuracy. So this shows that the models are kind of trying to have dependence on the language that is being trained on. So another kind of important point to note here is also that in this case, we took a vocabulary of 100,000 tokens. In this case, we took a vocabulary of 20,000 tokens, but the difference in performance is very little, which means that even by training on a smaller vocabulary, we are able to get like a good performance over here. And the advantage of using a smaller vocabulary is also that you can train it a lot faster than using a larger one. Another interesting thing here is that we also trained a model where we sampled from all different languages together, and we created a combined data set of around 1.4 million training and around 350K test samples. And even here, we get a pretty good performance of around 86% overall. And with the training accuracy of almost 90%. So this means that we are actually able to, these models are actually able to learn almost 9 out of 10 times they are going to give you the right result, which is pretty impressive compared to, given that these concepts are pretty high level and abstract. So how does it perform against traditional techniques? So in our previous study, we did not use deep learning for this, and instead what we tried to do is have models that were based on manual features, and where we use supervised learning techniques like logistic regression, perceptron learning, Adagrad solvers, and adaptive row vectors, and so on. But all of these gave us an accuracy of close to around 70 to 75%. Whereas the LSTM models here are actually performing almost 10% higher, 10 to 15% higher. So this clearly shows the superiority of using deep learning over traditional models. Another kind of study that we did as part of this work was to try to understand the hyperparameters that can be used for learning. So depending on how many units we use, we can get like different kinds of accuracy over here. So there's a lot of hyperparameters that could be used. So we try to understand what is the best set of parameters to use. And here we find that, so we performed 3 experiments where once we kept the LSTM layer fixed and modified the embedding layer units. Here we see that it kind of flattens out between 64 and 256 units and gives good performance for 32 and 512. When we do the opposite and keep the embedding layer fixed, we get the highest performance when the number of LSTM layer is 32. And then we also perform an experiment where we keep both layers having the same number of units and vary that. And we see that as the number of units increases, the accuracy increases as well. But note that this accuracy, the scale is pretty small. So it's not a very big difference. So based on these, we choose our hyperparameters to be essentially at this point where we take 128 units in the embedding layer, and we take around 32 units in our LSTM layer to do our training. So to give you some concrete examples of how well this model performs, here are some kind of predictions that are made by the model. So in this case, whenever the prediction score is more than 0.5, they are marked as actionable, and when it is less than 0.5, it's marked as non-actionable. And the good thing about the prediction score is that the higher the prediction score, the more actionable it is. So if you look at the last one here, so here the message says, "Hi, someone has hacked my Spotify and it won't let me listen to music because they're listening from another device. Please help." So this is a very highly actionable message because it has like a clear statement of what the problem is and a clear call to action. So this one is predicted as highly actionable with a prediction score of 0.96. Whereas if you look at the least actionable one, it's just something that says that Verizon CEO confirms interest in possible Yahoo acquisition. So this is where you're talking about, you're trying to find messages that are actionable for Yahoo, and this message mentioned Yahoo, so it came into the system. But here, it really isn't actually actionable from the customer service point of view, so it is marked as highly non-actionable with a very low prediction score. So here it shows that you are able to kind of get a very good gradation of actionability and non-actionability based on these models that are and the predictions. Another kind of set of examples is for the political leaning. So here in this case, a score which is very close to 0 is marked as Democratic, and a score higher, close to 1, is marked as Republican. And 0.5 is considered as the kind of boundary between the two classes. And in this case, if you look at the first message, it says that the contrast between Hillary Clinton's depth of foreign policy knowledge and experience with this gang is astonishing. And it has a few hashtags with "I'm with her" and GOP debate. So in this case, this is a highly democratic kind of a message because it supports Hillary Clinton and says that she's much better than all the other candidates. Now, this is something that is very easy for us humans to kind of understand, but for a model to understand this and mark it as democratic is a pretty impressive feat. And here, if you look at the Republican kind of messages you see here, between Obama, ISIS, Congress, welfare leeches, unfettered immigration, and liberalism, this country has gone downhill fast. So this is really kind of touches on a variety of issues, has a negative sentiment about those issues, and is marked as Republican by the model. So you see that as the score increases here, you see that the strength of the Democratic kind of prediction is lowered, and the strength of the Republican prediction is higher. The interesting thing is it also kind of finds out some moderate viewpoint. So compared to some of these messages here, which seem pretty extreme in their position, some of these positions are more moderate. So for example, this message says that Kansas oil producers are receiving less than $25 a barrel, and Obama wants $10 of it for his radical agenda. It is still kind of leaning towards Republican, but it is not as maybe extreme as some of these other Republican messages, and the model is able to capture that as well. The other interesting thing here is that here in the first message, you can see that the message indicates a certain candidate, whereas in the second message, there is no candidate mentioned. It's only a particular issue that is mentioned. So, and yet it is able to find that both are democratic in nature. So these are basically the kind of predictions that the model gives, which is, it seems like such models could be applied to a variety of other problems as well. So this shows a lot of promise. So some of the future work that we'd like to do is kind of extend this to maybe other kinds of problems. Another interesting thing to do is to understand these word embeddings that are generated by the model and maybe map them to certain clusters to figure out what words determine what kind of problem, what indicate what kind of problems, and then maybe explore different kinds of architectures for LSTMs and RNNs for doing this training. And also, in the case of political leaning, the models that were trained during, these models were trained during the early time of the primaries, which is very different maybe from a certain period now. So there is a kind of time dependence on when the data is collected and trained that would lead to maybe differing results in the case of political leaning. Yeah, I guess that's pretty much it. So any questions? Yeah.
Thank you for the talk. So you said that you've compared with the traditional supervised learning approaches, but I've missed whether you tried to first generate some good word embeddings and then just use something simple like logistic regression over those as one of the baselines.
No, in this case, the traditional methods did not use word embeddings. They were just created using manual features, things like, does this tweet have a question mark in the end, or does it contain a hashtag, and those kinds of manual features that were generated. And we have a previous study here, which you can refer to for more detail, that gives a list of around 30 features that we kind of created for this. But yeah, that's a great point. Maybe just using the word embeddings first and then running logistic regression might give better results than what we presented.
Yeah, but from our experience, it usually works really well, and you don't even need recurrent neural nets.
I see. Yeah, that would be good to try.
Thanks, a really great talk. So I'm curious, for the actionability, you checked multiple languages. Obviously, Democrat and Republican is very U.S. specific.
Yes.
So have you thought about looking at other countries, or particularly I'm curious about countries in which you'll have more than just a two-party system. So a lot of countries have a parliament system where you have multiple parties, and then your classification is going to get a lot more complex than just, which party are you?
Yeah, I think that's a great point. Yeah, in this case, like you said, we wanted to kind of keep the problem simple to solve. So we focused on the US, but the good thing is the same technique without any change in the kind of the model architecture could be applied to any other problem as well in terms of binary classification. You could also modify the loss function in order to have kind of maybe a softmax loss that would give you predictions over multiple classes as well. So I think, yes, I mean, trying it out on different kinds of data sets would definitely probably give as good as results as these, but yeah, it's you'll have to try it out.
And thank you also for contributing the data set to the community. Yeah. That's great.
Okay, thank you.